Welcome to the second day of the 2025 MEMS Summer School. Today, we're excited to host the two talks, beginning with ReaxFF tutorial presented by Nicolas Onofrio. He's a technical sales representative. Second talk will be given by Professor Masoud Madadelahi on intersection of microfluidics with MEMS. So first, let's welcome Dr. Onofrio as one of our invited speakers for this year's summer school. Dr. Onofrio earned his PhD in physical chemistry from University of Grenoble, Alpes in 2011. Over the years, he has held several academic positions, including serving as a visiting professor at Purdue University and assistant professor at Hong Kong Polytech University before transitioning into industry. Dr. Onofrio's career bridges academia and the industry, and his work exemplifies how cutting-edge computational methods and scientific visualization can drive innovation across disciplines. Now the floor is yours. Let's welcome Dr. Onofrio. Thank you.
Thank you, Peggy, for the introduction. Thank you, everyone, for attending the school, and thank you for the invitation as well. So so today I'm going to tell you about the software we developed in Amsterdam. So let me switch to full screen. So should be, let me know if there is any issue if you don't see full screen or slides not moving. So yeah, I'm really happy to be here to tell you about our software and how you can use it to model carbon-based material. So you can do a lot of things with the software, and I tell you just a little bit in a couple of slides, especially in terms of type of application and properties that you can calculate. But so what I want to tell you about today, so I'll start by sort of just an overview of a few properties you can calculate. So I picked up the battery cases because I've been working a lot over battery materials. And carbon-based material are very important in the battery electrodes, as you know. So I just give you a very quick overview of general properties that you can calculate. Then I'll move on and tell you about the history in a couple of slides of our company and how the software is constructed. And you'll see that we have many different compute engines, so you can address many different levels of theory with it. And after that, so this should take me 20 minutes, and after that I'll move on and I just pop up the software and I show you how you can build molecules, you can build crystals, how you can build like this nanoribbon that we're looking at here, and how you can deform it and extract mechanical properties. By the way, I found this very nice. So it's an amorphous carbon nanostructure. So it's a colleague of us that wrote these papers. So you have the reference here. So if you want to look up, so it wasn't done with our software, but you can easily do it with our software. And she's actually writing a tutorial to do this. It's a little tricky. So they use accelerated IDs, accelerated MD method to make it possible, basically to get this amorphous nanostructure, which is very nice. All right, so let's jump in. As I said, I worked on battery quite a lot. So there are a lot of properties that you can calculate with our software related to battery, right? You can calculate things like intercalation potential, how much energy it costs to put a lithium atom in the graphite, right, or in any oxide electrode. You can calculate things like activation energy. If you have a solid electrolyte, how much energy it costs for the ion to migrate in the electrolyte. If it's a liquid electrolyte, often you calculate things like a viscosity that's going to correlate with your diffusion properties. And then also interfacial properties like a reduction and oxidation potential that you can get with density functional theory. So you can cover really all the components of the battery, and I like this example because all those properties you see I'm showing, you can really compare them directly to experiments. So you're making a step of 10 order of magnitude between what we simulate here at the atomic level and experiment. You can actually compare things. Okay, so this is battery. Of course, there are many areas. So I haven't worked too much on polymer, but there are a lot of things you can do polymer. You can look at carbon base, also material in polymer and things like that. For the history, so we celebrated the company our 30-year-old this year, right? So company was created in 95. But the code was actually written back in the 70s, and so by Professor Barents and Professor Ziegler as well. And so what happened in between the 70, 80, 90 is like there was a lot of interest of private company in using the software, right? I'm citing some of them. So in the end, there was a need of a team to really support the development. So the company was created in the 90s. And nowadays, so we haven't grown too dramatically. We're just 30 people, right? So one extra person every year, basically, and mostly developer, right? So software developers. So the background in general come from physics and chemistry still, but those are people that are good with programming, and they implement new feature, they debug, optimize, document, support. So if you look at our website, so there's a lot of documentation, and really what you get with a commercial software like this, so there is a graphical user interface. So we really try to lower the learning curve for using this type of software, right? So if you have a PhD in computational chemistry, maybe you can use open source, maybe it's gonna be okay for you. But still, often you can sort of accelerate things with using this type of commercial packages because everything is going to be pre-made in there. But it's also great for people in the industry. So sometimes they just don't have this computational chemistry background, right? So they have the chemistry background, but not maybe the computational material science of chemistry one. So with this software, you can really learn very quickly and be able to do some advanced simulation. So I'll show you some example. So in the 70s, it was the DFT code, right? Molecular DFT, it was called ADF, you might have heard about. So it's the equivalent to things like Gaussian, but the idea with ADF, it was to use Slater type orbital and not Gaussians. So it has some advantages, especially for spectroscopy. But across the year, so we became more of a platform where we have many different levels of theory in one package, right? So most of them, so it's developed in-house, right? So we develop ADF. Band is just the extension with periodic boundary conditions, so you can calculate the electronic structure of material. Band is also based on Slater type orbital. So what we did, so we don't need to rewrite a new plane wave code, right? There are very good code out there. So we made an interface for quantum espresso. So you can also use it with our driver, which I talk about it in a minute. We also have semi-empirical method, DFTB, and then ReaxFF, which you've learned yesterday, I know, by the developer, right, Professor Van Duyn. And so today I'll show you example with ReaxFF. And then machine learning potential, so it's something pretty new that we try to integrate as much as possible because, you know, they give very good performance and very good accuracy, and we have also other force field. And this is just for the atomistic part because we also have methods, or we also have compute engine to look at things at higher level. So I won't talk about this today, but just that you know. So the way you talk to our software, there is a central driver, and this driver is going to be talking so it's going to be at the interface between the user and the compute engine that I just defined. And so it's something that's quite nice because there is one unified driver that can basically talk in the same way to all the different compute engines. So if you use different software, right, if you want to use maybe LAMPS and I don't know, Gaussian, because I mentioned it before, or Roca, input file are completely different. The way you do MD, you integrate equation of motion is completely different. So in our software, there's just one driver that really just get energy and forces from the compute engine. So with the driver, you can basically do molecular dynamics. You can move ions. You can do a geometry optimization, find the ground state of your molecule. You can compute phonons. You can do tons of things. So you can basically explore the potential energy surface with it. And the way you talk to this driver, so there's a graphical user interface, and that's what I'm going to use today. And there is also a Python interface. So you can do everything with Python. So that's really nice if you want to do much more complex workflows. Another thing, so what I mentioned before is well, with this type of tool, basically, there is a lot of things that have been predefined and that sort of help you to accelerate and not having to rewrite constantly or reinvent constantly. Like I would say, tools. So there's this molecular gun. You can basically apply velocity to particle, to group of atom, reaction boost. You can cross energy barrier. You can do net elastic band, of course. You can do potential energy surface exploration. We have bond boost, which is used for reactive molecular dynamics simulation, things like looking at a cross-linking polymer. And we have many other tools, right? I won't go over it, but a lot of it also related to electronic structure properties. So you can very easily visualize spectra, work function, etc. Okay, so that's good. That's a good start. That's just for the general introduction. Now, so you probably received an email. Otherwise, so I just give you a quick summary. What I can do, I can actually even post that into the chat. Let me try to find my mouse here. That you have it. So basically, the way it works, so you're going to download the software, and then what you can do, you can use this password. Let me see if I can put. Okay. So I put all of that in the chat. So anytime you can just get ready. You can download the software, as I said, and then you can use those credentials, and you're going to have access to our software, so to all the tools for 2 weeks. Now, what I recommend, so what I'm going to do, I'm going to demonstrate things. I'm going to open up the software, and I might go a bit fast. So what I recommend is you just follow what I'm doing, and maybe later on tonight you try to reproduce it, and you try to do some more advanced thing. And you can always let me know if you found something cool, or if you maybe in the future write a nice paper with our software. You'll definitely let me know. All right, so I'm going to switch. So once you've downloaded the software, it's going to ask the credential. You put the credential, and then you can basically open it up. It might ask you another time once you execute the software, and you will get to this AMS job windows. So for now, it's completely empty because I just went to a fresh empty directory. And as you can see, what it tells you to click the SCM button. And if you click this button, you're going to find a drop-down menu, and it's going to be all the tools that are available. And the one that we're going to use mostly is the input tool. So I'm going to switch to it. It's a bit annoying. I don't want to share my entire screen because it's too big, but I'm now going to stay to the input. So I'll share a last time, and we should stick to this one. All right, so that's what happens when you open a fresh input. So that's the main window, I would say, where you can build the atomic system, define the level of theory, define the different settings. And then the analysis is going in general to be other tool that I'll define, that I'll talk about it in maybe later. All right, so I'm going to do some general overview, right? So you see here we have ADF selected, and if you click on it, so you get all the compute engine that I discussed before, right? ADF, band, DFTB, and etc. So today we're going to use ReaxFF because it's just quite fast. So it's nice. So I can get to a result in a short amount of time. And then all the other tabs, they're going to be used for the settings. And the task here, it tells you how do you want to explore the potential energy surface? What do you want to do? You want to do a geometry optimization, molecular dynamics, and you see there are many ways to basically moving ions. So I'm going to show you how one can build some very basic atomic structure. There's also the periodicity here. So if you plan to just look at molecules, you can put periodicity 0. And again, so this is very consistent across all the compute engines. So because we are in like ADF and band, they have local basis set, you can actually work with 0D, 1D, 2D, 3D systems. Okay, so let's build. So I think I have a couple nodes. So I'm going to build propanol. So you see you have a few atoms down there. So you can either click on it. So you're going to select the carbon atom, or you can also click the C button on your keyboard. If I click once, so the carbon is created, and then it's trying to make a bond. So if you want to stop here, you just hit escape. And then you have your carbon atom. Now, when you want to select, in general, it's good to do shift and then to basically drag your mouse to select whatever number of atoms you want. And by the way, what I'm going to show you here, everything is documented. So by the end of the presentation, I'll share the PDF of the presentation with you. And you get all the link to be able to reproduce that at home, right? So don't worry if you think you're going to forget. I have all the sections that are relevant for this presentation in the PDF. All right, so propanol, so 1, 2, 3, and then I click oxygen, and now I have my oxygen. I escape, so I have the carbon chain, and I have the oxygen, and then I can select all the atoms, and there is a shortcut. So you do Command E, and it's just going to passivate it properly, right? It's going to look at the stoichiometry of those atoms, and then it's going to put the hydrogen. Now there is this little wheel at the bottom here, so it's a pre-optimization button. So what it's using by default is going to use UFF to just to do like a quick optimization of your molecule. So if I click on it, you see that it puts properly as expected, like the proper angle and bond length, which is based on UFF potential. You can, if you right click, you can actually use more advanced potential, even machine learning, if you want, for your pre-optimization. Okay, so that's a molecule, so you can go fancy. So there is a lot of things predefined, right? Alkyl chain, amino acid, etc., aromatic. So you can really build anything, metal complexes, different coordination, and etc. Now let's build a crystal. So for crystal, first you need to switch to bulk. And when you switch to bulk, you're going to see that in the command bar, you're going to have a new item, which is this little flake here. And the flake is just to reflect the periodicity of the crystal. You see now we have a box. So maybe I can build a diamond. So you can build from the geometry, you can build from the space group, or you can even search. We have a small database here. If you click the magnifier, so you can look at, for instance, graphite, you're gonna find some structure. I'm just going to use, well, I want diamond, right? So I use cubic, and I'm going to get a diamond cubic. So now it's asking me which element I want. I put carbon, and I get the unit cell. Very often, so it's more convenient to look at the conventional cell, right? So again, the snowflake, and then you can switch to conventional cell. Okay, so there is some shortcut. So if you command 1, 2, or 3, you can align along the 3 direction your lattice vector. So it's very convenient to look at it in the different angle view. There is a generate supercell. So that's the thing we often do, right? You want to make the structure a little bit bigger, right? So you do a 2 by 2 by 2. And finally, you can generate a slab, or you can, there is this shortcut here, this, how is it called? Parallelepiped shape. So this is going to make you a slab. And you can pick the direction. So diamond, we're gonna make a 1, 1, 1. And you can see the plane as well. So it's kind of nice view. And then you can generate the slab, and he went back to the unit cell and he gave me 2 layers based on the conventional cell. And that's what I've got. And now you see that he switched the periodicity to slab. So now we're 2D, so we only have 2 vectors. And you can go back and generate a supercell, but this time we just have 2 directions to replicate. Okay, so this is the view from the top. One thing that I can show you, so it's very easy if you want to let's say make a surface and a molecule adsorbed on it. So you can just go ahead, right? The same as I showed you before. You select the carbon. Let's say I want to put CO2 somewhere here. Then I want to put oxygen. I escape, and then I put another oxygen atom here. Select them. You can move it a little bit. So if you do right click and with some selected atom, you can move around. You can displace them around. So I don't know wherever we want to put it. I have no idea of CO2 on slab of diamond. But then we can do the same. We can do this time. So I have the ReaxFF engine. So I can do a quick geometry relaxation. So I'm going to basically minimize the forces based on this interatomic potential. So I don't go over the model because I know yesterday you talked about it. So it's just a many body potential. So the nice thing we have, so there is a library of ReaxFF that you can just find. So well, when you selected this engine, you see the force field here. And so we have about 100 of those force fields because the interaction is parameterized over a finite set of elements, right? It's not a universal model. And so what this does when you click on this is just going to pre-select all the force fields that contain the C, in this case, the carbon and oxygen atom. So you see there are many, but the CHO, I'm just going to use the CHO today here. So I have the force field selected. Now I can say, okay, just pre-optimize. Maybe what I can do, I can also tell, so in the geometry optimization task, I can go, so there is always this little triangle here next to several of the settings, and it gives you more options. And one thing I want to check here is to optimize the lattice dimension as well. And then I can hit this pre-optimization, or maybe I can actually save it, or I'll do it later. So you can see, well, CO2 went to its normal geometry, and then it seems like he moved away a little bit. So I'm sure I can put it closer, and maybe it's going to absorb, but this is another question. Okay, so we built a bulk crystal surface with adsorbate. So let's do now build a liquid or a gas. So we have another tool for that. It's called the builder. So you do edit, builder, and here basically what you can do, so you can set the density. You can set the box dimension, the number of atoms. So there are many ways for which you can define your box of molecules, basically. So I can make a water box. So I want 1 gram per centimeter cubic, and maybe 10 by 10 by 10. And then here you define the type of element. So either as a smiles, or you can look up in. So if I type water, you see that he has something in the database, but you can also just type the O letter, which is the smile string for water, and that's all. And then generate the molecule, and I think let's see what it does. All right, so it built this water box. Now the nice thing we can do, so this was quite simple, but I make maybe something a bit bigger. And then you can make mixture. So I can put methane because it's simple. And I can put maybe a ratio between the water and the methane. So let's see what it does. All right, so you can very quickly build your simulation box. So it's just based on PACMol, probably no. Let's do more. How about now we make an interface like a surface, and on top of it we're gonna put maybe some molecules like water, or we put something like this. So I think maybe I can go get graphite. So graphite, so here we have a few layer graphite, and maybe what I can do is I can increase, so model lattice. So here I have the lattice definition. So it seems like it's been optimized because it's got a lot of things. I just clean up a little bit the structure because this doesn't need. And then what I can do, I can open up the feed direction, right? So I can make this thing a bit bigger. I don't know, maybe 40. Right? And same as I did before, if I go back and if I take my builder, so I can actually do exactly the same, but this time you see the box dimension is predefined by what I've got here. And I can say, okay, maybe just keep the same mixture. Maybe we just do that. We can lower a little bit the density. And if I generate it, let's see. So he recognized that there was an actual material there, and so he inserted all the molecule in between. So you sort of have this mixture in between 4-layer graphite. And you can see what he got, right? So in the end, we have about 0.79 fraction of water for 0.21. All right, so yeah, that's what I can do. Maybe let's do some basic calculation with it before I switch to taking this nano ribbon and trying to calculate the mechanical property out of it, just to show you how you do a geometry optimization. So again, right, I can keep what I've got before. So what I did before, I did this pre-optimize, right? We basically use the temporary directory and run the calculation. But in general, what you do, so you want to save the calculation and then to run it via the other window, which is called AMS job. So let me do that. So I'm going to save it, and then I'll show you how it looks in AMS job. So graphite. And then we have water and we have methane, and I relax it with ReaxFF, like to be explicit. So I'm going to switch, so it's not very convenient, but at least I show you how things look like in the other GUI. Okay, all right, so now you can see the job is here, and the job is marked as sequential. So what this means sequential, so it's going to run locally. So I have a MacBook here. And if I have to submit another job, because I can submit many at the same time, sequential means it's going to wait for one to finish to run the second one in serial. What you can do, you can actually define queues. So you can define a queue. You can basically make a connection, SSH connection with a remote cluster, such that you can run it remotely, but you're still going to be able to appreciate what is happening on your local laptop, right? So it's like if you have the power of a cluster computer on a notebook. So it's very nice, but I'm just going to run it locally. So you just do job. So the job selected, job, and then run. So it's a geometry optimization. So there are several atoms. So I don't know if this is going to converge or so, but what I want to show you, so if you click I mean, we can see a few lines here, but if you click on it, you're going to have a pop-up and you can see the energy. So it's a geometry. So the energy is going to go down. You can probably have access to other numbers, right, related to the error in the force, the maximum of the force, the stress, because I'm also relaxing the box, and etc. So there is a nice tool which is called AMS Movie. So from there, if you do SCM and then you look at movie, I'll show you this pop-up here. So with AMS Movie, you can look at what's happening during the geometry optimization. So there is a slide bar here, so you can just move it with your mouse, or you can just play. So you see that the geometry has been actually quite deformed. So the angle of those three vectors is also changing. You have access to the energy, you have access to the gradient, so you can really appreciate. I think it terminated. You can really appreciate the geometry change. So yeah, we can see how the cell has been deformed. Now, one thing, so there are many things you can plot with AMS view, and so maybe I can show you a few. For instance, we were looking at I was talking about the lattice vector, so I can do graph and I can do add graph. So it's going to add an empty one here, and then in graph I can select lattice vector and I can look at maybe do we have. Yeah, we have angle, so I don't know, angle 1, 2, right? And you can see how this angle is probably the angle between vector B and C, right? So and you can see how these vary along the geometry optimization, and there are pretty much all the different geometry definition that you can appreciate. All right, so let's go back to AMS input. Here, switch one more time. And maybe just to finish up with the overview, I can run a molecular dynamics simulation. So here I have the final structure, which is maybe not really relevant. Okay, so the task now is going to be molecular dynamics. Then I look at more details, the number of steps. So I can do 10,000 steps, the time step. So for ReaxFF in general, 0.25 is a kind of the rough number you would start with. The sample frequency, so how often you're going to write the trajectory to the drive. And then the checkpoint frequency is how often you're going to write a restart. So the restart, let's say I don't care, I put a big number. I need an initial velocity for the atom. So I can just sample a distribution, right, to get a 300K velocity, temperature, sorry. So that's going to be the initial velocity, and I can also put a thermostat or a barostat, right? So I can couple the system with a reservoir to give it to control the temperature. Right? So let's say I put a thermostat, so you can put many of those. You can only thermostat some region if you want. So there are many things you can do. And so you can select, right? So I can take Berensen, so those are different type of thermostat. But in all those cases, even if you use Nose-Over, in general, there is a coupling constant that you need to define. And for, again, the rough big number, that the general number that you put is going to be 100 femtosecond. Sometime you might have to vary this number depending on your dynamics. But for general cases, this is just going to work out. So I put this thermostat, now I just save it, and let's have a look at the molecular dynamic simulation. So now it's an MD. I didn't put the temperature in the thermostat. So I put the initial temperature, but then the thermostat. Okay, it's saved. And I'm going to run it, and then I just switch directly to AMP's movie. Okay. All right, so you can look at it from here and the same, right? So we can play the movie and we can see the atom moving. We can look at different things. So graph, I can add graph again. I can look at, let's say, the temperature. We can see how the temperature, how the thermostat is quickly coupled, and we get to this 300K, quite stable, but there are many other things you can look at. Maybe one thing, so the volume is going to be constant because I didn't put the barostat, but then you can look maybe at the kinetic energy, potential energy, etc. All right, just going to let that run. Now I'll move back to the input, and then we're going to start working on the tutorial. So what I'm going to do, actually, I'm just going to start a new input. So there is nothing going on. So the idea was to make a nanoribbon. So you can do graphene, but graphene. So if you want to break graphene, you sort of want to have like a large number of atoms. I did some tests, and the small system, you're not gonna get like the nice properties. So I want to run something during the tutorial. So I want it to be finished. So I'll just make a nanoribbon, and nanoribbon, you get an idea on, and it's also interesting because you can vary many things, right? You can vary the width of your ribbon, you can vary the number of layers if you want, and you can see how Young's modulus, so I'm just going to do uniaxial deformation, but you can see how this affect basically the mechanical property of the material. So I just start with, again, right, you can look for graphite, you can build graphite. There are many ways of how you can start here. So we have this structure in the database, so you can start from it. Now I like to use this convention cell, so it's just going to align basically the A vector with the origin, sorry. And another thing which I also prefer to work with is to make it rectangular, right? So here we have a supercell with this 60-degree or 120-degree, so you can apply simple transformation to get to the rectangular cell. So basically you can use our generate supercell and you put the right transformation, which you just remember it, and you know that doing this transformation here is making a rectangular cell. Okay, so that's what we've got. And then we're going to look at just a monolayer. So again, I shift and then I drag the mouse around the atom, which I don't want, right? The second layer, and I delete them. Another thing that I'm going to do right away, so the lattice in the Z direction or in the C direction, I'm going to make it a bit bigger, maybe 30. Or maybe that's a lot, maybe 20. Okay, so we sort of have just a monolayer. So right now I have a monolayer of graphene, and then I can make it, so to make this ribbon, so I'm going to generate a supercell. So maybe something like, I don't know, 8, 1. It's a bit too much. Six, and here I make it a bit longer, 8. Yeah, even 10. That's not what I wanted to do. sorry. Actually, A, I want to deform it along A. So I'm going to make 10A. And then B is going to be the width of the ribbon. So let's say I put 4. And then in Z, I don't want to replicate anything. Okay, so I have something like that. And now I'm doing the same game. I'm going to open up the B dimension this time. So I go to the lattice, and here we have 17, and I'm going to put maybe 10 or 15 extra on each side, right? So if I put 15, I have 30, so I can put, let's say, 50 total, and that's what we get. And you can see the bond, because they were making bond across the periodic boundary condition. So they're still making bond. So what you can do, there is this tab which is called bond, and you can say guess bond. So it's going to re-guess the bond based on the new periodic boundary condition. So now I have a ribbon, and I can passivate the edges, right? So I can just select only the atom on the edge, and then I can do this command E to passivate, and I can do that on the other side. And that's how you build a quick ribbon with amps. Okay. So the idea is going to be to apply a deformation along this red axis, along A here. So I'm going basically to gradually change the periodic boundary condition and to increase that and map the atom. And so I'm going to need to measure the stress tensor, because then I want to do a stress strain curve to extract the elastic property. So what I need this structure to be at 0 stress, right? Because if I start to deform right now, the potential might give me a very big stress in A dimension. So the first thing I need to do, I can do an NPT molecular dynamics simulation to relax the stress up. So I do molecular dynamic, ReaxFF. I still pick the CHO force field. If I find it, it's here. And then, so I'm gonna put an initial 300 Kelvin temperature. Now I'm gonna run 100,000 steps. So I still don't need this. I'm going to sample every 1,000. I'll put a thermostat, so exactly the same as before. Berenson thermostat, 300 Kelvin, and then 100 femtosecond. So all of that is written in my slides, so you should be able to reproduce. And then the barostat this time. So I also use Berenson here. I put 1 atmosphere. The damping constant is in general, so it's a factor of 10 with what you put with the thermostat. And I'm just going to change to scale the X direction, right? So here we go. I can already calculate such that I don't forget later to calculate the stress tensor, right? So it's going to write it to the trajectory so we can do the analysis. And that's all. So I save. This is equilibration. Quill. Right. And then basically you just, so this is going to add it to AM's job, but as I selected the input file, I can hit command run, and it's just going to run it in the background. And what we want to look at this time, we want to look at the movie and see what's happening, and look at the stress tensor, look at the volume. So I'm going to switch one more time to the other window, which is AM's movie. And here we can appreciate the equilibration, right? So here's what happened. Now, if I look at the properties, so there are a few important things that we want to look at. So maybe we can look at the temperature. We can see how we equilibrate. You see that at the beginning, there is like a peak. So we go from 300 to 460 because probably the cell, there was a large stress on the cell, so the temperature went up. And then another thing we can look at is the pressure tensor, and I'm just going to look at the X tensor. So this is going to run up to 100 of those frames, right? Because I'm writing the trajectory every 1,000 step, and I run 100,000. So I'm going to have 100 of them. And we should get something equilibrated. Another thing you might look at, and if I look in this direction, I see it very well. So the nano ribbon, because it's just a freestanding string, basically, and I initialized the velocity at 300 Kelvin, but I didn't tell the software to have a zero momentum, right? So it has some momentum. So you can see the ribbon is kind of rotating. This doesn't matter, right? It's not going to affect anyhow the simulation, or at least if in a way that we have a big enough cell, it won't affect it. So whenever the calculation is finished, there is a pop-up. It's telling me, do you want to import the geometry? So I say no, because what I want to do, I want to select a geometry where the pressure is very close to zero, right? So by the end, which is well equilibrated, so I get this point, and then I'm just going to do file and update geometry in input. So now in the input, I have a well relaxed structure, and I can go back to it. All right, so now it's equilibrated. It's a little bit tilted, but it's okay. I'm just going to add the deformation, and we run that, and then we'll get to the result. So I'll run it a bit longer. So maybe I can remove also the barostat, right? I don't need the barostat. I'm going to do the deformation just in NPT, basically, just with a thermostat. And now I'm going to use, so if you do model, there is MD, advanced MD, and I can do deformation. And the deformation, so I can add a deformation. So there are a lot of things that you can do with this, but I'm just going to apply a linear deformation. And I'm going to put a velocity, a length velocity, basically in the X direction. So I did a little bit the math before, but if you calculate, if you know the time step, and if you know the length of the simulation, so I know that in 5 to the -5 angstrom per femtosecond, you should break this thing. That's pretty much all, right? So now I can save it again, and I can run it with this deformation. I think I didn't forget anything. So I run it a little bit longer. Okay, that should be fine. Okay. Okay, so now I'm going to switch a last time to the movie, and we can see what's happening. And maybe in the meantime, so I can tell you a little bit how we're going to extract the properties. Okay, here I am. All right, so now the deformation. So the deformation, actually, I made it kick right away. What you can do, so you can start the deformation a little bit after. So again, to thermalize properly the geometry. So right now I have 0 stress, so I'm good with the stress. But however, I still initialize the velocity with a new distribution. So you might want to, if you want to do more production calculation, you might want to equilibrate a little bit by not starting to deform right away. But we can already see the potential energies going up. So there's something happening. And if we look at the MD property, and I can look at the stress strain. So what this does, so it's just plot the stress in all the direction, right? It plot the stress tensor basically as a function of a direction that I selected, which is X, which is my deformation. And this is the engineering strain basically. So it's the deformation over the original, so it's a ratio, right? And so you can see that the stress in X, which is the direction I'm applying the stress, is going up. I'm applying the strain is going up. So again, it's a bit rotating, but another thing that you can plot think I have still a few minutes. You can look at the lattice vector number 1, and you can see how this is indeed linearly increased. Right? So we're doing the thing properly. So I just want to keep maybe 5 minutes for questions. So I'm just going to finish up by just showing you how. So whenever you get this stress strain curve, and if you've done a little bit of material science, so you know, right? So you can get the elastic property or this elastic, yeah, the elastic property to this uniaxial deformation. You're just going to do a fit. A linear fit of the basically 1 or 2% of the deformation, because that's the elastic deformation that you want to capture. So you can select the plot, right? I click to this middle plot, and then I can do a graph analysis. And here, so I select which curve, and it's the XX linear regression. I add a linear regression, and I tell it to finish somewhere around 0.2%. And it does the fit, it shows me the fit, and I have something like 32 GPa, which is my elastic property. Okay, so maybe I'll show you the slides now, and I can just finish up over there. I'll continue sharing. So this is what I've done, right? I've shown you like this overview things that you can build, and those are the links. So you can go to the documentation, you can reproduce what I've shown. This is how the kind of steps that I use to build the nanoribbon. So this is for graphene, but you should be easily able to do the nanoribbon. And if you have any problem, you just let me know. And then we do the deformation. So we have an example where we snap just a polymer, like a single chain of polyacetylene. This is the result. So if you let it run, so you're going to see that at one point it's just going to crack, right? So you get to this yield point. You can measure the yield strain basically, and then you can do the fit like I've done. Those are a few snapshots, so it doesn't break all of a sudden. So first we sort of make those chains, and then chains start breaking down. And so that's how you get the stress strain curve basically. So yeah, so now you have access to the code, so you can download and you can do it yourself. You can do everything. And thing that you should do is you should try first to reproduce what I did, but then explore other stuff, right? So what happened now with graphene, with multiple layer, how this mechanical property they vary. How about if you put defect, right? The defect, you just click, you just remove atom. It's very simple. With computer to do this type of thing. We can really do defect engineering. You can put oxide. So there's a lot of things you can play with in those 2 coming weeks, hopefully. All right, so I hope I just gave you like some idea of what the software can do. So we just look at one compute engine, which has ReaxFF, but there are a lot of other things that you can do. And so the idea really is to have this user-friendly interface that can help you to build atomic structure, do the calculation, and also the analysis all in one. So we have tons of documentation. I'll invite to check it out. And this is a few other links just to finish up. So we published a new paper that described the software recently. So this is the link here, and then you can get tutorial. If you have any question like technical issue, there's something you cannot do with the software, you can put a ticket. You can have pricing, so you get the pricing directly on the website here for academia. And that's all. And thank you all for your attention. And yeah, happy to answer a few questions if there is time.
Thank you very much for walking through the software. Now let's see if there's any questions from the audience.
I have a question. Thank you so much for such a nice introduction. The credentials which you shared with us, are these for the demo version, right?
Sorry, I didn't understand. Can you go again?
Sorry, I will switch my microphone.
It's better. Much better now. I also opened up my laptop because my laptop was closed and the speaker is inside. So please go ahead. Sorry.
Yeah, the credentials which you shared with us to download,
Yeah.
it's for demo version, right? Or free trial?
Yeah.
And
Yes,
for how long is it valid, and what are limitation of the free trial version?
so it's going to be for 2 weeks. So
2
15
weeks, okay.
Yeah, from the time that you start the demo, or I think it's maybe from today actually that she did it. But if you need more time, if one of you say, okay, I'm not done exploring the software after 2 weeks, of course you just send me an email and I put 2 more weeks for you happily.
And I know that the license, it depends on the many factors, but what the number starts at, like for academia?
The pricing, you mean the price?
Yeah.
So if you go on this link, you see you can get directly. Maybe if I click on it, I stop sharing. I can just show you quickly. Okay, where is it? It went on the wrong one. No. And I'm here. Yeah, so if you go to pricing and you scroll down, yeah, so the license is quite complicated. So it goes with points. So different module count for different number of points. And so, like we talk about ReaxFF, so ReaxFF is 1 point. And then if you scroll down a little more, so you have the table, because it also depends on the number of processors that you want the software on. So we have people, they just want the software on their laptop. So they don't want to pay the same as the supercomputer. So yeah, those are the pricing here in euros. So you see for 1 point, and you're going to look at this column if you're interested in ReaxFF.
Okay.
This is a one year price for academia.
Okay.
I kind of give you an idea, but if you have any other question, again, you just let me know.
Yeah, thank you so much.
You're welcome.
Hi, Nicolas. Excellent presentation. Thank you for the introduction. So one question I have is, we've done a similar modeling for loads. If we want to apply a shear load instead of, uniaxial, and the same graphene ribbon, how would you apply a shear?
So I believe you can do it. I haven't done it, but this is basically why like when I pop up this deform. So let me open it up. Yeah, so you see. Let me go back just very quickly one last time. Okay, AMS input. Yeah, you see, you can directly put like a target lattice. So basically, you can put a shear if you want. You can add it. That's how I would do it. Basically, I would put this target, but maybe there are other way you would do it. Well, you can, if you put number right in A and B at the same time. I mean, if you put velocity in A and B at the same time, you're going to apply shear. I haven't done it, but I'm sure you can do it.
Okay. So one more question. So in terms of machine learning applications, any quick word on that?
Sure. So the way it works, so we have this machine learning. So what we've done, so we've integrated a few models. So you can see them here, right? So ANI, they're quite popular. They were one of the first model. So it's good for like organics. So there are different flavor of ANI. So 1x, 2x, so they can be reactive. So those you can just, select it and just directly play with it. And M3GNet, it's a universal graph neural network. IMNet2, so those are some interesting models. So there we ship it. But it's not all, right? So you can actually use pretty much any machine learning potential. And the way this works, so we have an ASC engine. So most of the machine learning model people, when they develop it, they make an ASC calculator. And so what you can do, you can basically hook up the ASC calculator to our software. So it's just going to use the driver, so you can still do all those complex tasks and deformation and things, but it's just going to query the energy and the forces from the machine learning model. So the answer is you can really use like pretty much anything, any model out there.
Okay, thank you. Thank you.
Are there any limitations for certain materials or conditions?
Yeah, like to be fair, so we are not a large scale like model. So if you want to do like really big molecules, you know, like the one I was showing maybe in my first slide, those very big structure with millions of atoms, you better use lamps. Probably it's going to be more efficient. However, if you work with more like medium-sized material, like 10 of thousands of atoms, our ReaxFF is actually much more efficient. So yeah, so we target more reactive material. So we don't have those very fast force fields like Bromax or you know, we're more on the tens of thousands of atom limit, I would say, with the classical model, of course. That's one limitation I think of.
My next question is, do you have a library or a community to share the information models and the troubleshooting for students if they want to use this software?
Yeah, so the way we do, so we have the support ticket system. So that's how we work. So we used to have, I believe, I joined 3 years ago, and I think it was already over. But we used to have a forum, like a mail, and yeah, it went kind of dead. So right now, yeah, the best contact is via support. So basically, all the developer, because those code we implement ourselves, right there. So the developer directly answer a question to the user, but we're really active, right? So I take care of dispatching support tickets. So we answer like about 100 support tickets per week. So in general, we have about 10 developers which are active at the same time. So it's like a ticket, like a several tickets per day for each other. So we spend in general a couple hours in the morning to do that. So yeah, you're definitely going to be in touch with us if you need to. Yeah.
Thank you. Any other questions? Let's thank you again. Thanks, Dr. Onofrio. It's an excellent talk, and thank you for walking through ReaxFF. I'm sure the MEMS community will have a lot of things to discuss, and hopefully we can collaborate and do some excellent work. Thank you.
Thank you very much.
Thank you.
So our next speaker, Masoud, are you here?
Yes,
Yeah,
I'm here.
please.
Hi.
Okay. Can you share your monitor?
Yes. Sure.
Masoud, are you okay with recording?
Yes, yeah, hi.
Great. Thank you.
Okay, let me introduce Dr. Masoud Madadelahi. He is a research professor in the Department of Engineering at Tec de Monterrey since 2022. Tec is one of the leading research institutions in Latin America. And Tec group is one of the important groups in the MEMS network. Masoud has a research group focused on design, fabrication, and testing of lab-on-chip and lab-on-disk platforms, which applications including DNA amplification, cell separation, etc. And he has been integrating a diverse microfluidic unit on the lab-on-chip and lab-on-disk platforms. Before joining Tec, he's a postdoc researcher. First, he earned his mechanical engineering PhD degree as a collaboration between Sharif University in Iran and Delft University of Technology. His expertise is in micro and nanofluidic systems. Let's welcome Dr. Masoud Madadelahi to give us a seminar. Thank you.
Thank you, Dr. Peggy, for your kind introduction. Hello, everyone. It's a pleasure for me to be here. I am supposed to talk about some of my research work about different applications of carbon materials in microfluidics. But before that, I would like to show you my team. Actually, many of following slides are coming from my students' work. This team is working on microfluidics, specifically on centrifugal microfluidics, and also different applications of sensors in microfluidic devices, including optical and electrochemical sensors. You can see some of my selfies that I took, like, I think now it is 6 years ago, with Dr. Mark Madhu and Dr. Sergio, who are my mentors. And you can see some of our collaborators. Luckily, we had the opportunity to establish very good collaborations with different universities and research centers. You can see we have some collaborators in Canada, Germany. Like Spencer is a startup in Sweden. Even NASA in US, we established a very interesting microfluidic related project. Belgium, DTU in Denmark, and also FEMSA, that is a famous company here in Mexico. Well, today I want to divide my talk into 4 main sections. The first section is an overview on microfluidics. Because I don't know the background of audience here, I decided to have a few slides to go over basic concepts in microfluidics, which are actually helpful in the following slides. Then I'm going to talk about carbon applications for fluid manipulation in microfluidic systems, and also cell and particle separation, because I think the focus of this summer school is on modeling. So I decided to have 2 modeling examples to show you the procedure to have such simulations and modelings in microfluidics. Then I thought probably this will be too boring to have many equations and theories, so I decided to add a few interesting side applications of carbon in our projects. One is related to PCR or gene amplification. That is very interesting, I think. There I have both modeling and experimental results. And the last one is about carbon application in microgel generation using microfluidics. I'm going to show you some experimental results here to explain the interaction of such nanoparticles with cells and the advantages that you can have using such nanoparticles. And at the end, I will have my conclusion. Well, I think you know the meaning of microfluidics. Any fluidic system in which we have a scale or dimension from tens to hundreds of micrometer or below 1 millimeter is a microfluidic system. Our human circulatory system is a very good example, in which we have our vessels with microchannels, and blood is the working fluid there. But in a lab, we have something like this. That is called lab on a chip. We have a plastic chip, or we can have different materials like glass, plastic, and so on. we have tiny amount of our sample, and we usually have some electronics. For example, optical sensors or electrochemical sensors. This package is called lab on a chip because we can replicate what we can do in a conventional lab in such a small scale like this. And it is very clear that it is a multidisciplinary field where we have a combination of engineering, nanotechnology, biotechnology, and chemistry, and also physics. Why do we need microfluidics or lab on a chip? Well, there are many advantages. The most important one is that we will have reduced sample and reagent volumes. In some cases, they are very costly, so it's very important to manage the cost of your project so you can do whatever you do in a conventional lab on a very small scale and reduce the samples or costly reagents that you're using in your project. The process is very fast. Fabrication is very fast. Usually you can fabricate and even test one microfluidic device in one day. It's not that expensive. Of course, it depends on the applications or sensors, but usually they are cheap. They are portable. That is very, very important. And also you can automate this process. And by this automation, you can reduce the human errors in your analysis. This field is not that much new. You can see that we can consider the first start point in 1840 by the introduction of Hagen-Poiseuille equation that is very famous in fluid mechanics. Then in 1990, we have this invention of microtest devices by Andreas Mons. And right now we are moving towards human on a chip, organ on a chip, and then human on a chip. From research point of view, I extracted this diagram recently. You can see that we have this increasing trend in the number of publications. So we can consider it as a hot topic. And from commercial point of view, I was looking for a recent diagram yesterday to have it in my presentation, and I was surprised when I saw these numbers. But you can see the huge market of this industry that is increasing year by year. So from both research point of view and commercial point of view, this topic is very, very popular. And I had the opportunity to meet Andreas Mons last year in Mexico City in our conference. He is retired now, but he talked about his first experiments to shape this field. That was very, very interesting. Okay. In microfluidics, we have different platforms. You can see them all here. But today, I would like to focus on 3 of them because of our limited time and also my background and related research that I'm going to present. I want to focus on pressure-driven microfluidics, centrifugal microfluidics, and electrokinetic-based microfluidics. I think pressure-driven microfluidics is something very well-known, you know about that, where we have a pressure source, usually a syringe pump, or we can use pressure controllers to make a pressure as a driving force in our microfluidic system. But centrifugal microfluidic, that is my main research field here, is a family of microfluidic in which we do not use such syringe pumps. Then how can we move the fluid inside our system? We use such devices. We can use a stepper motor, or we can use a servo motor, or even a very cheap DC motor to spin such disks and to generate different forces, mainly centrifugal force, as a driving force. And then we can manipulate a fluid inside some microchannels on that spinning disk. What are the advantages of centrifugal microfluidics? Well, one important one is easy multiplexing. The second one is automation. This platform is very, very good for automation. It has less complex fluidic interconnections, and it is very cheap. Specifically, if you can use a DC motor, you don't need to go for syringe pumps, which are pretty costly. From research point of view, here you can see the number of papers published on this topic, centrifugal microfluidics. Of course, it is a part of microfluidics, so it is not that much, but it is going up year by year. Interestingly, we can electrify such rotating disks. These electrified disks are called electrified lap-on disks. How can we do that? Well, we have three options. We can use batteries, something like this. You place a battery on that disk and then you rotate it. You can use some coils for wireless power transition. So this is another type of electrifying lap-on disks. And the third option is slip rings, where we have some specific tools to electrify that rotating shaft. Why do we need to electrify these disks? Because in that case, you can combine centrifugal microfluidics with some other microfluidic platforms, specifically electrokinetic-based microfluidics. I think you're familiar with electrokinetic-based microfluidics. We have three main families. One of them is electroosmotic flow, in which we have fluid motion induced by an applied electric field. When we have such microchannel like this, in which we have a conductive fluid, if you connect this microchannel to a DC voltage, because of electric double layer that we have on the wall of that microchannel, you can move the fluid inside this microchannel, and it is called electroosmotic flow. It has some advantages and disadvantages. Well, one important advantage is that here you do not have any moving parts, but it has some other disadvantages, right? For example, you have a limited velocity range in this case. One important difference that we have between normal velocity profile in a microchannel and electroosmotic flow is that unlike this parabolic velocity profile that we have in a regular microchannel, in electroosmotic flow, we have a block-shaped velocity distribution, which is basically flat. Next family of electrokinetics is called dielectrophoresis, or DEP, which is a movement of polarizable particles, usually cells or some nanoparticles, in a non-uniform electric field like this. We can have it as positive or negative DEP. Positive DEP is the case in which particles move towards regions of high electric field, something like this. Here we have more electric field than here, so this particle moves in this direction, and the opposite case is called negative DEP. One of the most important applications of this DEP is for cell separation or cell sorting. I have an example about this for you in our next slides. And finally, we have electrophoresis, where we have some charged particles, for example, DNA or protein, in a uniform electric field like this, and those particles can move, right? Depending on the charge and also mobility, they can move in that field. One important application of electrophoresis is called gel electrophoresis. And again, I have some experimental results on this topic in my following slides. Okay, now what is the role of carbon in such electrokinetic-based microfluidics? For all these different applications, we need electrodes, right? Depending on the performance of that electrode, stability, and also geometry, we have different options. I have listed some of them here. For example, platinum and gold, they are very popular electrode materials, but they are very expensive, right? ITO is another candidate, and carbon is another possible material that we can use as electrode in such microfluidic devices. Similar to other materials, it has some advantages and disadvantages. For example, it is not expensive. It can be flexible, right? It has, in some shapes, it has high surface area. It is electrochemically stable. In many cases, it is biocompatible. And we can have it in different forms, right? For example, carbon ink, glassy carbon, carbon nanotubes, and so on and so forth. In this table, you can see different applications of electroosmotic flow. I want to start from electroosmotic flow and the way that we can model it in microfluidic devices. So you can see that we can use electroosmotic flow for microreactors, for microenergy systems, for cooling systems, for electrokinetic mixing, and also diagnostics. If you are interested to any of these applications, you can find a complete list in our review paper. But today I want to focus on this application in one modeling example that I have for you. I want to use this electroosmotic flow in a micromixer. So we have a micromixer like this. It is a regular T-shaped microchannel. But in the middle here, we have this chamber. And in the middle of this chamber, we have this conductive hurdle, as you can see here. You can see different parameters and dimensions. We have our electric field applied to this conductive flow here. And as the electrode, we can use carbon material, as I explained. So this is our geometry in this simulation. The next step is finding the governing equations. Here I have the complete list of governing equations for you. The first one is Navier-Stokes equation. The plus term on the right-hand side is the term that we have because of that voltage, applied voltage, right? Where we have electric field multiplied by charge density, or rho E. That is our driving force or body force in this equation. The next equation here is continuity for the fluid, because this fluid is incompressible. It is a liquid, so we can have it like this. And the third one here is Laplace equation to find the electric potential distribution in our domain, right? So logically, we need to solve all these equations all together in a system of equation. You find this electric potential distribution. Using that, you can find electric field. You put that here, and you find the velocity distribution. But we have another option to simplify this procedure a bit more. How? First, I want to introduce this equation here that is called Debye length. Using this equation, you can calculate the thickness of electric double layer in your system. You can see the list of parameters here. Usually in microfluidic systems, this electric double layer thickness is something negligible. That is very, very thin. And considering that this rho E, or net charge density, is something exists in that thin electric double layer, so I have this option to neglect this body force here, solve this Navier-Stokes equation, but instead of a no-slip boundary condition over these walls, I apply a slip velocity boundary condition because of that neglected electric double layer. How can I find that slip velocity boundary condition? Here you can see the equation that is very famous, Helmholtz equation. That is a function of applied electric field. So here you can see the involvement of that electric field in our regular Navier-Stokes equation. And we can solve all these equations by other boundary conditions, right? For example, we consider ambient pressure or zero relative pressure at inlet and outlet. And this is the boundary condition that we consider on all channel ones. And finally, we need to solve this equation. C here is the concentration. And this is convection diffusion equation to calculate the concentration of species that we have in our microchannel. To solve this system of equation, we usually use COMSOL multiphysics. That is a very well-known software these days. So you don't need to discretize these equations yourself. You can just select these equations and use that software to solve these equations. Well, the first step in any numerical simulation, as you know, is validation of your results. And for that, we usually use some experimental works. Here you can see our reference to compare or validate our simulation results. Here we have another EOF micromixer. You can see the PDMS material here. Here we have two inlet channels, and this is our outlet, and this is the space in which we place two electrodes, like this. And this is an experimental work to show the concentration distribution inside this microchannel. Here we have one concentration, for example, 1. Here we have 0, and here we have something between 0 and 1. And this is our simulation results. You can see that it has a pretty good agreement with the experimental measurements. Here you can see the concentration distribution along the channel in two different positions, 502 millimeters. and you can see the like accuracy of this model, right? After this model validation, the next step is applying your own geometry. That is something like this. You need to discretize this geometry. And then you can start doing a parametric study. For example, here you can see the effective number of hurdles in this micro mixer. We have 2 hurdles, 3 and 4 with different configurations, different angles. We quantified this mixing phenomenon using this parameter that is called mixing index. It's a parameter that is a function of concentration in that microchannel. You can see that for example, for 2 hurdles, we have this 45 degree as the optimum angle, something like this. But by changing the number of hurdles, that alpha changes, right? For example, with 3 conducting hurdles, we have this maximum mixing efficiency, and for 4, we have this one, right? You can capture the effect of like dimensions of that central hurdle. For example, in a circular shape, we can call it Ri, and the outer radius is called Ro. And again, you can capture that mixing efficiency using different Ri to Ro ratios. You can even capture the aspect ratio of the micro mixer in total. You can see how it improves by increasing the aspect ratio of this microchannel. And here you can see the vortices that we have around this conductive hurdle. And because of these vortices, actually, we have our mixing in this device. We also consider different geometries in this micro mixer. For example, here we can consider different geometries for the central hurdle, circle, square, and triangle. And for the chamber, we consider similar shapes. And you can see that the maximum mixing efficiency appears here when we have circular geometry for the hurdle and triangular for the chamber, something like this, right? And then you can even go for time-dependent or transient modelings to see the mixing index versus time, something like this, right? This is our proposed EOF micromixer, and this is mixing in a conventional T-shaped micromixer. And you can see that it is faster, right? And at the end, you have a better mixing if you use this EOF micromixer. As I told you, you have the possibility to integrate this EOF on a spinning disk or centrifugal platforms. Here, you can see a list of different publications in which we have either analytical or numerical simulation of EOF under the effect of centrifugal forces. If you're interested, again, all these references are available in this paper, so you can find many more examples on this topic. Now, as a second part of electrokinetics here, I want to talk about EP and DEP. Again, in this table, you can see different works published on electrophoresis. The most important one, as I told you, is gel electrophoresis, and I have some images for you in our following slides where I want to talk about PCR monitoring. And for DEP, again, we have many applications. As a second example, here I want to focus on this one, DEP for cell separation. And this is the model that I want to explain right now. Here we have a centrifugal microfluidic device, as you can see here. We have this micro channel there, and we have some electrodes like this, right? This is our inlet, and we have 3 outlets. Using DEP or dielectrophoresis, we want to separate different particles in this microfluidic system. We have polyestyrene beads, we have yeast, we have red blood cell, and also platelets in this simulation. You can define different parameters. For example, this radial distance is delta x. This angle is called alpha here. Omega is the angular velocity of this spinning disk. And of course, we have voltage, geometry, number of these electrodes, and so on and so forth. From experimental point of view, this spinning DEP is something feasible. And for that, as I told you, you have those 3 options, right? Battery or induction or slip rings, right? And then you can connect the electrodes that you have in your microchannel to positive and negative poles, and then you can have DEP while that disk is rotating. Okay. Again, we need to find our governing equations to have this modeling. You can see them all here. The first one, this equation is Navier-Stokes equation, right? The first one is continuity. Body force here is called F, where we have centrifugal force and Coriolis force, which are coming because of that rotation. Then for particle tracing, you need to solve second Newton's law, that is here, right? This is basically that sigma F is equal to MA, that famous equation. For sigma F, you can consider, or you should consider, all important forces applying on those moving particles in your system. Centrifugal force is very important. Coriolis force is another important force. We have drag force. Here we use Stokes' law, that is a famous drag force equation for spherical objects. And finally, DEP, or dielectrophoretic force, that is defined using this equation. This E is our electric field. dP is the diameter of particles that we have. And this KCM is Clausius-Mosotti factor. That is a parameter, very important parameter in this equation, and you can define it based on epsilon values like this. Okay, here you can see the list of parameters that we have considered in this simulation. For that DEP force, we need to find this factor, right? KCM, or Clausius-Mosotti factor. For that, you can find different models. For example, we can have double shell models or single shell models. In our following slides for yeast particles, we have used double shell model, in which we use these 2 equations to calculate epsilon, and then we use that epsilon here, right, to calculate this KCM, and then we use the real part of that here to calculate the EP force. And for red blood cell and platelets, we use single shell model using this equation. And you can find such diagrams. If you don't like such equations, you can use such diagrams to find that real part of Clausius-Mosotti factor, and then you use that for the EP force. In this simulation, as I told you, we considered only drag force and the EP force, right? Besides rotational forces, we considered only drag and the EP. But in general, we have more forces. For example, lift force is very, very important if you want to do particle tracing in your modelings. It is highly recommended to consider different lift forces in your simulation. But of course, that depends on the microfluidic device that you have. For example, we can have Magnus lift force, where you have particle rotations. You can have Safman lift force, where you have pressure difference around those particles, shear gradient, and wall-induced lift force. For example, this wall-induced lift force is a kind of lift force that we have in vicinity of our channel walls. So it is much better if you can include these different forces in your simulation. You can have a better or more accurate results, right? Okay. Now that we have our governing equations, let's go for model validation. For this model validation, we use the experimental works from Dr. Martinez and Dr. Madhu, who are the organizers, interestingly, organizers of this summer school. As you can see in this experimental work, we have some carbon electrodes like this, which are fabricated using pyrolysis. So we use SU8 and photolithography technique to make such structures or features. And then we do pyrolysis to have glass-like carbon like this, right? And then you can place these electrodes, carbon-based electrodes, in a microchannel like this. Here we have our inlet, and this is the outlet. Using these electrodes, we want to filter yeast particles from latex particles. Because for the first one, we have positive DEP, and for the second one, we have negative DEP at this specific frequency. Frequency is very important here. And as the driving force here, we use a centrifugal force, right? So for the validation, first, we apply this geometry. Like this, we have these different cylindrical electrodes. You need to discretize it. You need to do mesh independence analysis to find the exact number of grids that you need in your simulation. And then you need to replicate that experimental work and compare your results with that experimental work, right? As we did here. Here on this vertical axis, you can see filter efficiency, which is defined like this. And on the horizontal axis, we have flow rate. And you can see a pretty good agreement between our simulation and experimental results. Right? And this is our own geometry that we want to analyze after this. But before we focus on this, on this new geometry, even for that experimental work, you can do a parametric study and you can optimize some working parameters, right? For example, here, if I can play this for you, here you can see different particles, polystyrene beads, dead yeast cells, and live yeast cells. These are our electrodes, and you can see how they are trapped here, right? When we have this low flow rate, 5 microliters per minute, we have almost 100% separation efficiency. But by increasing that flow rate, eta decreases, right? Which makes sense because we don't give enough time to those particles to be affected by this electric field, right? And they can pass through these electrodes without trapping. And here you can see the corresponding RPM values. Middle column here shows the velocity field distribution. And on the right-hand side, you can see particle trajectories or path that we have in different cases. This is actually the advantage of modeling, right? You cannot see such details in experimental analysis. And you can do basically whatever you want, right? For example, you can see the effect of different configurations of those electrodes. Here you can see different number of rows that we have from 1 up to 5 and see the separation efficiency, right? Here you can see that when you have only one row of those electrodes, separation efficiency is only 8%. But by increasing that number, you can achieve to 40% more or less. And it makes sense because we are increasing this electric field area, right? So we affect those particles and we can trap them in this area. You can also consider or analyze the effect of those electrode dimensions. As you can see, by increasing the size of those electrodes, we have a negative effect in filtering efficiency or separation efficiency. Why? Because we will have these empty gaps in which we do not have any electric field, so we cannot affect those particles. And by increasing the number of electrodes, you can increase that filtering efficiency. This was the maximum filtering efficiency that we could achieve, 58%. Okay. Now, let's switch to our own geometry, our main geometry that was something like this. I want to show you the effect of dP versus centrifugal force. The first case is when we have a uniform velocity distribution in our microchannel like this. Here you can see the top view of that microchannel. When you turn your centrifugal force on, centrifugal force and also Coriolis force appear, right? Like this. So we will have this change or deformation in our particle trajectories. The opposite case is the case where we have dP on, right? And we have this opposite behavior for particles. And when you turn both of them on, then we can have this focusing, right? So you can focus all those particles in your spinning DEP device. And you can even measure that deflection precisely. Again, this is not that much feasible in experimental analysis, but in modeling, you can do whatever you want, right? For example, at different RPMs, you can precisely measure the effect of Coriolis force on deflection of such polystyrene particles. Then you can study the effect of different other parameters. For example, radial distance, tilting angle, that alpha angle, microchannel width, and omega, which is the most important parameter here. You can find the effect of these parameters on flow rate and consequently on DEP force and separation of particles, right? For example, here you can see 4 different radial distances from 2 centimeters up to 5 centimeters, and you can see the number of particles that we have at different outlets of this microfluidic device, right? For example, in this case, when we have 50 radians per second, we have 100% focusing in this microfluidic device. And by increasing the number of electrodes, again, you can have a better focusing because, again, by increasing that number, you are increasing the effect of that DEP, right? So we can go even up to 2 or 3 micrometers as the focusing width. And at the end, you can consider more scenarios, right? For example, instead of having all those electrodes on one wall, we can have this pattern for that. And again, you can repeat what we did. You can capture the separation efficiency, right? Or you can put them on top wall and bottom wall like this if you want to affect them vertically. And that is again feasible. And finally, for some biological applications, we used this simulation to show the feasibility of RBC and platelet separation. The point is that at some specific frequencies, like 100 kilohertz, that KCM factor, or Clausius-Mosotti factor, is negligible for platelets. So you can use this fact to separate RBC from platelet, right? So you can use this frequency like this. You can affect RBC particles or red blood cells more than platelets to have such separations, right? And at different rotational velocities, you can have different separation efficiencies. And the other important thing is that we can even separate live and dead yeast cells by adjusting that frequency again, right? So at 1 megahertz, again, we use that change in DEP force between these two particles to separate them like this. And similarly, for different rotational velocities, you can have them like this. Okay, so this was my second example for electrokinetic-based microfluidics. It was, as you saw, it was DEP on electrified lab on disk device. Similar to any other devices, here we have some advantages and disadvantages. For example, one important advantage is that we do not need external syringe pumps, right? Because of that DEP method, you can use that for uncharged particles, which is label free, right? It is portable, it is rapid, and for that, we can have low voltages, right? But negative effects on the other, or negative aspects of this device is that probably the design is a bit challenging. And for that, we need that on-disk AC requirements, right? This was an example for DEP on disks. We can have other types of electrokinetics on disk also. You can see the list of advantages and disadvantages here. Again, if you are interested, because I don't have enough time, we have a complete list of those studies in this review paper. Okay, now I want to change the topic. I want to talk about carbon material applications in PCR systems. First, let's look at the meaning of PCR. I want to give you some basics about that. You know that PCR, or polymerase chain reaction, is a method to amplify genes, right? I think you have heard this keyword during pandemic, and this is a very well-established biological procedure. Here you can see the components of a DNA. In each DNA, we have a sugar phosphate backbone connected to some bases. We have 4 different bases: adenine, thymine, cytosine, and guanine, which can be connected together using some hydrogen bonds. A connects to T always, and G pairs with C. So this is the structure of a double-strand DNA. How can we amplify such DNA fragments or pieces? For that, you need to have a PCR solution where we have these different components. We have DNA sample or DNA template. We have our primers, forward and reverse primers. We have nucleotides, which are actually these 4 components. We have a polymerase. Tag polymerase is very famous for that, for regular lab procedures. We have a buffer, and we need a PCR tube, right? So you basically mix all these components in this PCR tube, and then you place this PCR tube in this machine that is called a thermal cycler. Why do we need this thermal machine? Because for this PCR, we need to apply a temperature cycle 30 to 40 times, or basically 20 to 40 times, depending on your application. Using this machine, we can have 3 different temperatures. Denaturation, which is the first temperature, is typically in this range, 90 to 100 degrees, is a temperature that we use to separate those 2 DNA strands, right? So we will have 2 single like pieces of such sugar phosphate backbones. Then in the annealing step, which has this temperature, 50 to 65 degrees C, we can attach our primers to those DNA pieces. We have 2 primers. Usually we have forward and reverse, like this, to be connected to 2 ends of those DNA strands. And finally, we have extension around 72 degrees C, and we let this polymerase to make this DNA piece. So we can consider this theoretical amplification, right? In each cycle, we multiply the number of DNA strands that we have by a factor of 2. So after like 30 cycles, we will have this number, right? But this is very, very theoretical. Basically, in real cases, we cannot achieve to this number. Why? Because we have something that is called inhibitor. Inhibitors are different factors that actually inhibit reaching this final amplification, right? But good news is that on the other hand, we have some facilitators which can help us to increase this number, right? And nanoparticles act as one of the best facilitators in PCR systems. How and why? The most important thing is that they can increase the thermal efficiency or temperature distribution that we have in a PCR solution, right? So we will have a better thermal cycling in that system, and consequently, we have a better amplification. But they can also interact with different components that we have in a PCR solution. For example, they can interact with polymerase, that tag polymerase, to be more stabilized, right, at high temperatures. So it works more efficiently. They can interact with primers to decrease their melting temperature and improve the specificity of this process. And finally, they can interact with double-strand DNAs in a way that this denaturation happens better, right, more efficiently. For this specific application, I mean, using nanoparticles as facilitators of PCR, you have many options. You can use metal nanoparticles, you can use carbon-based nanoparticles, and many other options, right? You can find the complete list in this paper, where we processed, I think, more than 200 papers to find the range of different nanoparticle size that can be used in PCR procedure. Here you can see that number for different materials. For example, for AU, which is very, very popular, we have this wide range of different publications. And for different carbon-based nanoparticles, we have these ranges, right? For example, here you can see different shapes of carbon nanoparticles, right? And optimum concentration is shown here. For each nanoparticle, we have an optimum concentration for that PCR process. Again, carbon nanoparticles are here, metals are here. So you can find the best concentration for each nanoparticle. Now, let's look at a real experiment to show the effect of carbon-based nanoparticles in a PCR amplification. Here, I want to present one of our works that is a microfluidic-based PCR device to amplify genes. And there, we use diamond nanoparticles. In this device, we have this droplet generation chip where we generate these particles. Inside these particles, we have those PCR components plus diamond nanoparticle as a kind of facilitator, right? And then those particles go all the way through this tube, very long tube. It was like 9 meters, I think, to experience those 3 temperatures: denaturation, annealing, and extension. And here you can see the SEM image of that diamond nanoparticle. Of course, you can have different droplet sizes like this. For example, here you can see water fraction that is 0.3. Here we have very small droplets. And by increasing that water fraction, you can go to liquid plugs, right, in your channel. And then we use this system to capture the mixing that we have in these droplets. You can see that here we have a blue color, red color, and at the end we have this purple color, showing that we have a proper mixing because of secondary vortices that we have inside these droplets. It is very important. Why? Because as I told you, in these droplets, we have diamond nanoparticles, and it's very important to avoid sedimentation, right, in these particles, in these droplets. You can also do some numerical simulations. As you can see here, inside those moving droplets, we have these secondary vortices, right? And these are actually helping us to have that mixing in those droplets. And interestingly, they are changing by time, right? For example, this is one pattern, another one is like this. And you can also see the velocity magnitude there. Here it is another modeling that we did to find the droplet generation system. And this is the experimental results. These tiny points here, they are our droplets coming out of that system. And this is the outlet. Well, for that, we established a new fabrication method for our microfluidic device. I think I can skip it. I don't know how much time do I have, Dr. Peggy?
Maybe 5 minutes?
How much, sorry?
5 minutes, if you
Okay, sure.
can, can summarize quickly?
Yes.
Yeah.
Then I can skip that slide. For the final results, this is that gel electrophoresis that we used in this project, where we have this agarose gel connected to a positive and negative of a power supply, and DNA pieces can move inside that electric field, right? So you can see the effect of different concentrations of that diamond nanoparticle on PCR efficiency after 20 cycles and also 25 cycles. And you can see that we can actually amplify that PCR efficiency by a factor of 5 if we add those nanoparticles. We studied the effect of DNA concentration. We also compared it with some other nanoparticles like TiO2, and we compared the results with conventional PCR devices, and we could show that we have almost the same results, and our device was 40% faster. Okay, and as the final part of this research, I wanted to talk about carbon application in microgels. Microgels, I mean some microstructures made of some hydrogels, for example, gelma or alginate, which are very soft and fragile hydrogels. You can add carbon materials to those microgels to enhance some properties or to add some fluorescent properties to these microgels. For example, here we added NGQD to gelma to introduce some fluorescent characteristics to this hydrogel, and we could show that this characteristic is very, very stable for even more than 7 days. We use that in this microfluidic device where we have NGQDs plus C2C12 cells, which are muscle cells, and we made such microgels, right? You can see this fluorescence image here because of that NGQD, and we also did some mechanical tests. We could show that adding NGQD can increase the viscosity of that hydrogel and also make it more elastic. And interestingly, we saw that adding NGQD to such microgels can enhance cell viability after 10 days. So you can see that you can use it as a fluorescent dye to your system, and it has a positive effect on your cell viability, right? That is great. Okay, I think I can skip this part and show you this final work. Well, this is another work that we did. Again, we used NGQD, but instead of GELMA, we used chitosan and also alginate to make such core and shell structures. Here in this core part, we use NGQD as a fluorescent dye to have such images. And we could encapsulate C2, C12 cells in the shell and E. coli in the core part. And I think I can jump to this slide, and you can see that after 15 days, we have a very high cell viability in our system. So again, it shows the application of NGQDs as fluorescent dyes in this system without affecting cell viability there. Okay, so as the conclusion, we know that carbon materials combine biocompatibility, conductivity, and structural versatility that makes them ideal for integrated lab-on-a-chip systems. 3D carbon structures can be used for different electrokinetic-based systems like UF, EP, and DEP, and we can consider carbon as a low-cost electrode material. We can use these particles in PCR systems to improve thermal conductivity and consequently PCR yield or efficiency. And we can use them in microgels as fluorescent dyes to improve the cell viability. There are more applications. I didn't have time to have more. For example, electrochemical sensors in microfluidic systems is another interesting field that we are working on. Okay, at the end, I want to thank my team for their efforts. Here you can see some of our featured publications, and I want to thank all the sponsors that help us in this procedure, and I want to thank you all for your attention.
Thank you very much, Masoud. Congratulations for excellent work. You have been doing a lot of work in the microfluidic field.
Thank you, Doctor.
I'm very impressed about your program. I want to ask a quick question about what do you think about the CD microfluidic platform, which has been studied for maybe over 30 years, right?
Yes.
And we all know they have very clear advantages. Simplicity, scalability, and integration potential to a lot of other applications. What's the major, why commercialization adoption has been slower than expected? What do you think about that?
From commercial aspects?
From commercialization aspect. What's the main hurdles?
Yeah, main hurdles there. Well, I think in general in microfluidics, we need more time to see more commercial devices. But specifically about centrifugal microfluidics, probably because people or researchers are not familiar with spin stands and the way that they can use this rotating platform for fluid manipulation is a big hurdle to advertise this field and to attract more researchers working on this field. From commercial point of view, I think it has a lot of potential. Here, for example, we are working on a project with a famous company that is called FEMSA for water analysis, where we are combining electrochemical sensors and also optical sensors on a centrifugal microfluidic platform to have rapid PCR. So the idea is to do a very fast PCR in less than 15 minutes on that portable device, right? Again, if I want to sell this device to you, I can focus on some negative aspects of other microfluidic platforms. For example, in all these electrokinetic-based microfluidics, we need a power supply, right? Which is a very, in my opinion, it's a negative aspect or hurdle that we have in those platforms. But here we have a small motor that is cheap. It is portable. Automation is very important, right? That is available on this platform. So comparing with other platforms, I think the centrifugal microfluidics has a lot of potentials and advantages to be commercialized in near future, hopefully.
Thank you.
Thank you.
So let's see the audience. Please ask questions.
I have one quick question,
Yes, please.
if time allows. So when you were in your second simulation, where you were trying to validate the work of Dr. Martinez Duarte, you had the red blood cells and the white blood cells separation. I wanted to know, how did you set the boundary conditions for those 3D electrodes? You had 3D electrodes in the validation, and then you had 2D electrodes in the actual your experiments. So just wanted to understand like how we usually set up the boundary conditions.
Thank you. Thank you for your question. Well, all our simulations there were in 3D. I mean, geometrically, they are 3D.
Okay.
In this model, let me show you quickly. Yeah. So here, you can see the positive and negative voltages that we have, right? And for the channel wall, we considered insulation, and we consider the same or similar pattern for the other geometry.
Okay. So the electric voltage boundary conditions for the one on the top, was it set at the bottom, or were it given directly to the walls of the electrodes?
To the walls of the electrodes, because there we didn't include the electrodes themselves, right? This is a pure fluidic, let's say, modeling. So in that sense, the material that you consider for those electrodes is not playing a role that much, right?
Okay, so then how was the separation possible without setting without including the electric field work into it, means?
No, yeah. So we do have electric field in our simulations, right? Because we are applying that voltage over the surface of these electrodes, and then we will have electric field. This is electric field distribution, right? That we have in our system, and that electric field makes that like DEP force, right? And that DEP force goes to particle tracing or Newton's second law equation to affect the particle trajectory.
Okay. Thank you.
Thank you.
Any other questions from our audience? If not, let's thank both speakers for today's session, day 2 of our summer school. Very excited to see all this modeling work and experimental work from, Masoud group, and also the work through the ReaxFF software. I believe there's a lot of opportunities for our community to work on both aspects, experimental and modeling work. Sam, are you here? And Matthew,
Yes.
any announcement?
Well, I mean, the summer school is going very well, and I think we have highlighted the importance of simulation in terms of whether it's material discovery, in terms of understanding our processes, or in terms of newer applications. And I think that's the big lesson from this. And I'm happy that the attendance is good. And tomorrow we have a session specifically on innovation, IP protection, business development, etc. So I really would like to encourage our young scholars to attend that so that they have a complete understanding of what we're trying to do at this AxelNet. So Peggy, thank you very much for leading an excellent session today, and we'll see you guys tomorrow.
Also-
Matthew has some
Yes.
announcement.
Okay, so 2 things. If you don't plan on attending tomorrow's session, there's a link to a survey that you should fill out. And also, we want to take another group picture. We're going to try and do that every single day. So if everyone could put their cameras on, that'd be nice. And give it a few minutes. Okay. I'll just wait a little bit longer. Just waiting for Borzu, maybe. Okay, I'll just take it now. 3, 2, 1, smile. Okay, that's all for
All right.
me.
Thank you very much. See you guys tomorrow.
Thank you.
Bye.
See you all. Bye-bye.
Bye-bye.